Hi my dear friends, my name is Abhishek and you are watching Maths Magic channel on YouTube. Today we are going to discuss topic number 1.3 that is real numbers and their decimal expansions. In the theory, they have told you that real numbers are classified real numbers when described in or given in decimal expansion. On the basis of that we can describe we can distinguish whether the number is rational number or irrational number. For that they have given three examples, that is 10 by 3, 7 by 8 and 1 by 7. The explanation of all the three sums are given in example number 5. So we will move to the question number example number 5. Find the decimal expansion of 10 by 3, 7 by 8 and 1 by 7. So when we do the division of 10 by 3, we will get the quotient as 3.333 and so on. It will continue. So 3 3s are 9, 10 minus 9 that is 1. Again we are taking 0. So we will put point here. 3 3s are 9. Again we are getting remainder as 1. Here also 1, here also 1. 3 3s are, then we are taking 0. 3 3s are 9, 10 minus 9 that is 1. So here also remainder 1, here also remainder 1, here also remainder 1, here also remainder 1. Remainder are same, so quotient is also same. But the value of remainder are same, the value of quotient is same. Here second question is 7 by 8. 7 by 8 is given. So when we divide 7 by 8 we are getting, so here 7 is less than 8, so we will take 0. When we take 0 here, we will put 0 here and then point. 8 8 is 64. 70 minus 64 means 6 is the remainder. Taking 0. 8 7 is 56. 60 minus 56 that is 4. Taking 0. Then 8 5 is 40. So we are getting remainder as 0. So after some steps the division ends because here remainder is 0. So no more further division. Third question is 1 by 7. 1 by 7. So 1 by 7 in this we get, here 1 is less than 7, so we will take 0. When we take 0 here, we will take 0 here. So 0 and then point. So 7 1s are 7. 10 minus 7 that is 3. Taking 0. 7 4s are 28. 30 minus 28 that is 2. Taking 0. 7 2s are 14. 20 minus 14 that is 6 as the remainder. Taking 0. 7 8s are 56. 60 minus 56, 4 is the remainder. Taking 0. 7 5s are 35. 40 minus 35 that is 5. 5 is the remainder. And then taking 0, we are getting 7 7s are 49. 50 minus 49 that is 1. So again we are getting remainder as the 1. We have started from 1 and we are reaching at the 1. So after 6 digit the repetition starts of the quotient and the remainder also. So from these three cases they have given you the theory. Here they have taken the remainder or written the remainder, that is 1 1 1 in the case 1, that is here also 1 1 1 1. Divisor is 3. Divisor is 3. Case number 2. Here remainder is 6 4 and 0. 6 4 and 0. Divisor is 8. Divisor is 8. Here remainders are 3 2 6 4 5 and 1. 3 2 6 4 5 1. Again 3 2 6 4 5 1. Divisor is 7. Divisor is 7. So they are writing three conclusions from the three examples, that is remainders either become 0 after a certain stage or start repeating it themselves. After some point the remainder will be 0 or it will start repeating. Here as 1 is repeating and here after 6 digit it is repeating. Second step is second conclusion or second result they are obtaining is remainder is always less than divisor. I have written it very simple. In the book it is written very complex manner. It is written in very complex manner. The number of entries in the repeating string of remainders is less than the divisor. It means that the value of remainder will always be less than the divisor. Or you can simply write it as remainder is always less than divisor. Here divisor is 8, remainder is 6 which is less than 8, remainder is 4 which is less than 8, remainder is 0 which is less than 8. Here remainder is 1 which is less than 3, 1 less than 3, 1 less than 3, 1 less than 3, 1 less than 3. So in all the cases, remainder is always less than divisor. Here 3 is less than 7, 2 is less than 7, 6 is less than 7, 4 is less than 7, 5 is less than 7, and 1 is less than 7. So in all the cases, remainder is always less than divisor. That is the second conclusion or second result we are getting from the three results. And the last one is, if the remainders repeat, then we get a repeating block of digits in the quotient. Here 1 is repeating in the remainder, 1 is repeating here, 1 is repeating here, 1 is repeating here, 1 is so the quotient is also repeating 3, 3, 3, 3. Here after 6 digit remainders are repeating, so after 6 digit quotient is also repeating. So these three conclusions are the main things we have to remember in the decimal expansion of real numbers, that are rational and irrational. So we are discussing here the decimal expansion of real numbers. So they have given the final statement: on division of p by q, two main things happen: either the remainder becomes 0 or never becomes 0, and we get repeating string of remainders. Then they have discussed two cases. First one is about the when the remainder is 0. Here 7 by 8 example is given. Here we have taken the division 7 by 8, so we are getting remainder is 0. The same example is done here. Whenever we divide 7 by 8, remainder becomes 0 after some steps, so the answer is 0.875. Then they have given the example of 1 by 2, the answer will be 0.5. And then they have given the example of 639 by 250, the answer will be 2.556. So in all the three cases, after some points or after some calculation or after some digits, the calculation stops because the remainder is becoming 0. In all these cases, the decimal expansion terminates or ends after a finite number of steps. We call the decimal expansion of such numbers called terminating. Case 2 is discussed, in which remainder will not become 0, but it will repeat or recur after some points. In the example 10 by 3 and 1 by 7, we notice that the remainder repeat after a certain stage, forcing the decimal expansion to go on forever. Decimal expansion will go on until you want to carry it out. In other words, we have a repeating block of digits in the quotient. We say that this expansion is non-terminating and recurring. Here decimal expansion will continue. In 10 by 3 we have got the result 3.333 in the quotient, and in 1 by 7 we have got 0.142857, again 6 digit 14287, again 6 digit 142857, and so on. This way it will continue forever. So we got that this is non-terminating and recurring or repeating. So usually we write repeating 3 in quotient 10 by 3 as 3.3 bar. Here 3 digit is repeating itself continuously, so we will write 3 bar, and in 0.142857 we will put the bar on all the 6 digit because these 6 digit are repeating continuously. This is discussed in the theory. Then they have written the form of 3.5727272. So here 72 is repeating itself, so we will take the bar on, or we will put the bar on 72 because these two digits are repeating. Now on the basis of the above calculation, we come to know that decimal expansion of rational number are mainly classified into two things. First one is the terminating decimal expansion, and the second one is non-terminating and recurring decimal expansion. Then they have discussed two examples, that if we have 3.142678, then it is a terminating decimal expansion, and another example is 1.272727, and so on. 3 digits are there, 3 dots are there, so it is continuous up to infinite numbers, up to infinite times the repetition takes place. So this is non-terminating and recurring. So these both the decimal expansion are called as the rational number. Then they have discussed example number 6 on the basis of this two conclusion, that the rational number will be terminating decimal expansion, and rational number also consists of non-terminating recurring decimal expansion. Here they have told you, show that 3.142678 is a rational number. In the other words, express 3.142678 in the form p by q, where p and q are integers and q is not equal to 0. Here after 3.142678. Here after a point 6 digits are there, 1 2 3 4 5 6, 6 digits are there, therefore we will put 6 zeros in the denominator after writing 1. Thus it is in the form of p by q, where q is not equal to 0, hence it is called as the rational number. Then they have discussed question number example number 7. Show that 0.3333 is equal to 0.3 bar, because 3 is repeating itself, can be expressed in the form p by q, where p and q are integers and q is not equal to 0. Here we have to show 0.3333 in the form of p by q. Here we have already discussed the rational number. Here terminating decimal expansion is also a rational number, and non-terminating recurring decimal expansion is also a rational number. We know that the form of rational number is p by q, so we have to write this non-terminating recurring decimal expansion in the form of p by q. So we will go through the method which is given in the book. Here we have been given 0.3333 ... means infinite quotient is given. So we will suppose x is equal to, or we will assume x is equal to 0.33, because we don't know what is 0.33 in the form of p by q. So here one digit is repeating 3333 continuously. So here we will multiply with the 10, because in 10 1 0 is coming after digit 1. So multiplying 10 on both the side in equation 1, we will get x into 10, that is 10x, 10 into 0.33, that is 3.3333. So 10x is equal to 3 plus 3, 0.3333. Why 3 plus 0.3333? Because 3.3333, when we deduct it from 0.33 or the original form, when you deduct 0.33 from 3.33, we are getting 3 as the answer. So putting 3 here, we are getting 10x is equal to 3 plus 0.33. 0.33 is the assumed form of x, so we will put the value of x here. So 10x is equal to 3 plus x, making right hand side go to left hand side, or taking x from right hand side to left hand side, that is here it is positive, when it goes to this side it becomes negative. 10x minus x, so it will be 9x is equal to 3. So x is equal to 1 by 3 or 3 by 9, that is 1 by 3. So this is the answer, or the p by q form of 0.3333. Question number 8, that is show that 1.2727 is equal to 1.27 bar can be expressed in the form p by q, where p and q are integers and q is not equal to 0. We will suppose x for 1.2727. Here two digits are repeating, so we will multiply with the 100, two zeros after 1. So 100x, x into 100, that is 100x is equal to 1.2727 into 100, that is 127.2727. Therefore 100x is equal to 126 plus 1.2727. From where does the 126 came? So when we multiply 100 with 1.2727, we get 127.2727. 127.2727 minus the x, that is 1.2727, we are getting 126 as the answer. So we will put 126 plus x, because 1.2727 is nothing but the assumed entity, that is x. So 126 plus x. Here it is positive, when we take right hand side term into left hand side, we are changing the sign. Here it is positive, when we take here it will become negative. 100x minus x, that is 99x is equal to 126. Therefore x is equal to 126 upon 99. So 42 3s are 126 and 33 3s are 99. Then 14 3s are 42 and 11 3s are 33. So cancelling 3 we are getting 14 upon 11. So this is the final answer of or p by q form of 0. This is the final p by q form of 1.2727, that you can check by the calculator also. Then we are moving to the question number or example, solve example number 9. Show that 0.2353535 is equal to 0.235 bar can be expressed in the form p by q, where p and q are integers and q is not equal to 0. So we will assume 0.235353 as x. Here bar is upon 3, 5. So 2 digits are repeating. So we will multiply with 100. That is 2 zeros after 1. So 100 into x. 100 into x, that is 100x. And 100 into 0.235353, that will be 23.5353. So we are getting, when we subtract 0.235353 from 23.5353, 23.5353 minus 0.2353, that is x, we are getting 23.3 as the answer. So we will write 100x is equal to 23.3 plus 0.235353, that is 100x is equal to 23.3 plus x. So when we take right hand side down to the left hand side, the sign will change. 100x minus x, that is 99x is equal to 23.3, bringing 99 from multiplication to the division into the right hand side. And when we remove the point, we will get 0, we will get 10 in the denominator, that is 99 into 10, that is 990. So we are getting x is equal to 233 upon 990. Then they are discussing the theory that every number with a non-terminating recurring decimal expansion can be expressed in the form p by q, where p and q are integers and q is not equal to 0. What they are telling, that non-terminating recurring decimal expansion can be expressed in the form of p by q. Then they are discussing definition of rational number. The decimal expansion of any of a rational number will be in the form of terminating or non-terminating recurring decimal expansion. Or you can also say that the decimal expansion which is terminating and non-terminating recurring is also called as the rational numbers. On the basis of this, all the statements and the calculations which we have carried out, they are writing one statement for the irrational number. That is, if the rational number has the decimal expansion of terminating and non-terminating recurring, then the decimal expansion of irrational number will be non-terminating and non-recurring. This is the result we are getting from all the calculations above. So we can write the definition of decimal expansion of irrational numbers. That is, decimal expansion of irrational numbers will be non-terminating and non-recurring. Or we can also say that whenever the decimal expansion of a number is given as non-terminating and non-recurring, the number will be irrational. Then the last theory they are discussing before example 10, that is, they are telling you to suppose that s is equal to 0.10110110 and 410. So this is non-terminating and non-recurring number. So we are taking s, that is irrational number, is equal to 0.10, 110, 310, 410. So which is non-terminating and non-recurring. So it is called as irrational number. So one statement they have written that we can write infinite number of irrational number on the basis of number we have taken as s, or we can generate infinitely many irrational numbers similar to s. Then they have given the value of root 2, that is 1.4142135623 and so on. And they have given the value of pi also, that is 3.14159265386535 and so on. So they write one very interesting step here, that generally we are writing the value of pi as 22 by 7, but in actual case pi is not equal to 22 by 7. That is because it is approximate value, it is not exact value. Then they are discussing the Sulba Sutras. It is one of the Vedic treatise on the rules of chord during the 800 BC to 500 BC period, in which the calculation of root 2 is described. That is, root 2 is equal to 1 plus 1 by 3 plus 1 by 4 into 1 by 3 minus 1 by 34 into 1 by 4 into 1 by 3. The answer is 1.41421156. Here we can see that 1.41421, 5 digits are repeating. That is as same as the 1.41421, which is obtained in the current times or in the modern times with the latest equipment in the mathematical field. So it is exactly same up to 5 decimal places. So now we will use this statement that we can write infinite irrational number from the number or similar to s. Here we have taken the number s is the irrational number. So we can write same number like or similar numbers of the irrational numbers to s in the example number 10. Find a irrational number between 1 by 7 and 2 by 7. We know that 1 by 7 is 0.142857. So 2 by 7 will be 2 into 0.142857, that is 0.285714. To find an irrational number between 0.142857 0.2857, we will take the number after 0.142857 and before 0.2857. Here they have taken the 0.15, that is coming after 0.14, 0.150, 1500, 1530, 1540 and so on. So this number is an non-terminating and non-recurring number. So what they are discussing in the theory, 1 by 7 and 2 by 7, we find a number which is non-terminating and non-recurring lying between them. Of course you can find infinitely many numbers. This same number is obtained from the theory which we have discussed here, that is 0.10110, 1110, 410 and 0. So my dear friends, here our theory and example number, here we have discussed up to solve example number 10. So thank you and have a nice day, my dear friends. Repeat it 3 to 4 times so that you can have a great grip on the examples. Thank you.